So here's a reminder of what we did yesterday. So we focused on the rheology of complex fluids in yesterday's talk. So I started by giving an overview of complex fluids and of their deformation and flow properties, or rheology. And then I talked about theoretical approaches to modeling them from the continuum level. And in particular, I said that typically one would have a Stokes equation extended with a stress that accounts for the viscoelastic contribution to the stress from the mesostructures of the complex fluid, the polymer chains, the worm-like micelles, the liquid crystalline rod-like molecules. And that stress tensor depends on microstructural variables in the fluid, such as the orientation of the chains, the degree to which they're deformed, their alignment, and so on. And then one seeks to then write down an equation of motion for how that entity relaxes in the absence of flow, but also builds up in the presence of flow. So those are the basic equations that we talked through. And then we used a particular example of that, just because it's a particularly neat example that can easily be written down, the so-called reptation reaction model of worm-like micellar surfactants. And we first of all did what we call zero D rheology, and by that I mean confining everything to be homogeneous, so in 0 dimensions. And we talked in particular about the concept of the flow curve, or the constitutive curve. That's the shear stress, the force per unit area on the wall in this direction, as a function of the imposed shear rate. That's the relative wall speed normalized by the gap size. And we saw that this so-called reptation reaction model of worm-like micellar surfactants predicts a rising stress and then a falling one and then a rising one again at high shear rates. And we posed that this looks puzzling because it's trying to tell us that a faster flowing system has less stress. And we then suggested, first of all, that the resolution to that is that the flow doesn't stay homogeneous. So now this is going into a 1D calculation where you allow spatial variations in the one spatial dimension y, the flow gradient direction, that you then get the coexistence of two bands, a high shear band and a low shear band, with a stress that's uniform across the gap and common to both of them. And we actually worked through an analytical calculation in sort of pen and paper format on the slides yesterday to show that that's the case in the context of a very simple model. So that's where we got to yesterday. I'd actually hoped to finish this section on the rheology of complex fluids in terms of bulk instabilities yesterday, but I didn't quite do that. I'm sorry for that. So I'm just going to finish that off today by now moving from this one-dimensional picture where we allow spatial variations only in the y direction to ask what happens if we allow spatial variations in the x direction and the z direction into the board, which of course any experimentalist in practice is stuck with anyway. So now moving to 2 dimensions. So I'm separately going to think about 2 different 2-dimensional calculations, one in the XY plane. So we allow variations in Y, of course, the banding direction, but also in the flow direction. And then separately, I'm going to allow variations in the usual banding direction, but then also in the Z coordinate in and out of the board. Okay, so here's some experimental data from the lab of Sandra LaRouge in Paris. And as I said, these rheological experiments, so I've been drawing these flow cells so far as though we have perfectly flat plates and we sandwich the fluid between them and we move the top plate relative to the bottom one. Of course, as I've said, the top plate would eventually fall off the end of the bottom one. So the way that you usually deal with that is to have actually very large concentric cylinders. I can't really even draw them on the scale of this, but you can imagine cylinders going round. And so here we're just seeing a small chunk and there would actually be a slight curvature here and here. And so here we are actually seeing that. So now here the flow direction is round in the R direction. The gradient direction the flow direction is round in the theta direction. The gradient direction is in the R direction and the neutral or vorticity direction is in Z. And so there's a worm-like micellar surfactant in the flow cell and it's being sheared at some rate that's governed by how quickly the inner cylinder spins around. And then what Sandra LaRouge did here was illuminate this plane here with a laser sheet to image the cell as time goes on. And these are snapshots over time as a function of the vorticity direction, so the direction along the cylinder, and which is the so-called apparently neutral direction, although you can see now it doesn't turn out to be so neutral, and the banding direction y. So let's look in more detail at these snapshots. So and these are snapshots at these different times here. So what you can see is that quickly, on the timescale of a second or two, we indeed get a shear bands form. So the high shear band shows up as brighter here, and the low shear band as darker. And that, as I say, happens quite quickly, and it happens on the timescale of just typically a relaxation time or two. So tau subscript r, this basic viscoelastic relaxation timescale of the fluid, or maybe 10 times that, but at least on that scale. And then on a much slower time scale of about 100 relaxation time, so 20 seconds to up to 100 seconds, you see actually something else happens. So far we could capture this by a 0D calculation, this by a 1D calculation, allowing spatial variations this way. But now we have to allow 2D variations to allow for the fact that along the interface, we get these ripples or disturbances or waves that then form and settle to have a characteristic wavelength here. So we now need to do a two-dimensional calculation where we allow spatial variations not only in the flow gradient direction, which here is being denoted R, because of the curved flow cell, I normally call it Y, and in the vorticity direction Z. And the information that we might seek to capture out of that calculation is the timescale at which the interface destabilizes, and also the wavelength lambda, which is the wavelength between peaks of the ultimate ripples in the eventual state. So how are we going to do that? You'll have to excuse me because here I've actually changed planes now. These experiments are in the flow gradient, usually called the Y direction, and vorticity direction Z. Here I've drawn my sketches in the flow gradient direction and the flow direction X, but in fact the comments apply to either really. And remember that what we did yesterday in predicting whether an initially homogeneous shear state that's zero-dimensional would give way to a one-dimensional banded state is we represented the flow state in the system as a zero-dimensional base state to which we added small amplitude perturbations decomposed into Fourier modes in the Y direction, and we asked whether those modes grow or decay according to whether growth rates omega are positive or negative. So we do essentially something very similar here, except now it's a little bit more complicated because what we're thinking about here is an initial state that is the one-dimensional shear banded state where things do depend on the flow gradient direction Y. So we now have a base state which is shear banded and depends on the gradient coordinate Y. And now we add to that, we do a linear stability calculation where we add to that small amplitude perturbations, now with an eigenvector that is in fact an eigenfunction that depends on Y, but now decomposed into Fourier modes, either e to the iqx as drawn here in the X direction, or alternatively, and more suited to these experiments here, e to the iq subscript z into the board. And then because this is a linear calculation, we have the time dependence that's exponential and characterized by these growth rates here. And here I've just written down one Fourier mode. Of course, we have all the possible Fourier modes. And the thing we want to find out is whether these eigenvalues, so these are eigenvalues and the eigenfunctions emerge from the calculation. We want to know whether they're all negative, which would mean that any fluctuations decay away to leave a flat interface between the bands, or whether these perturbations with wave vector in the X or the Z direction grow to take you away from the flat interface state to an interface that has undulations along it. So we do essentially the same procedure as before, where we take our governing equations. Actually, here we've used a model that's called the Johnson-Sageman model, which is basically a phenomenological equivalent of the reptation reaction model. I don't believe that difference to be important, actually. We substitute this assumed form of the solution into the model, and we do an expansion, just as we did yesterday, where we expand to 0th order, 1st order, and higher order in these perturbation terms. The higher order terms of order delta squared are small, and you can effectively ignore them. And so once you've linearized the equations, you have some indeed linear equations in the amplitude of these perturbations here. That gives you what's effectively a big nasty matrix problem once you've discretized in the gradient direction Y. And out of that big nasty matrix problem, you can calculate the eigenspectrum, and you're interested always in what is the largest, most positive, most dangerous mode. And when we do that, we find that, so we get a so-called dispersion relation. Now, this is for the calculation where we have the wave vectors iqz into the z coordinate, into the board. So here's the dispersion relation of the largest, the most dangerous eigenvalue as a function of that wave vector qz. And what we find is that at high QZ, the modes are all stable. So stable is below 0 here and unstable is above 0. Whereas there's a window here where the eigenvalues are positive, and that tells us that perturbations with wave vector into the board would then grow if they have a wave vector in this range here. Now there's a mysterious, apparently showing 3 different dispersion relations here. That's because, as we talked about yesterday, we need not only the basic local form of the model, but also need to add spatial gradient terms into the model to account for the slightly diffuse width of the interface between the bands here. So that's this slightly diffuse width here. And as one might expect, if you have a more diffuse interface, that tends to stabilize the interface against forming undulations along it. And so as that parameter gets larger, we can actually restore stability. But in physical practice, we expect that wavelength to be very small. And this is expressed in units of the gap size between one plate and the other. So what we find here then is that we indeed get a positive growth rate. And the associated timescale with that is, of course, the inverse of the growth rate. And we find that it's of order 100 times the basic relaxation timescale that's in the constitutive equation of the model. And we find that the wavelength, because this is all expressed in units of that relaxation time, lengths are expressed in units of the gap size from one plate to another. And so 1 here means that the wavelength is typically of order the gap size. And that's indeed what Sandra saw in her experiments. She saw the timescale for the growth of these undulations to be about 100 relaxation times, and the wavelength to be roughly of order the gap size from the inner plate to the outer plate. Okay, we can also then, so that's a linear stability analysis where we take the governing equations, we have a simple one-dimensional base state, we add two-dimensional perturbations decomposed into Fourier modes, but that's still, once we're looking at each Fourier mode, that gives us a matrix problem, which the size of that matrix is basically how finely numerically we discretize the grid in the y direction.
Can I ask a quick question?
Yes, please.
So does the width of the shear bands in the y direction, is it always half and half? It looked like in the experiment that it changed. So I'm wondering if that affects the linear stability analysis in any way.
Yeah, that's a good question. Thank you. So let me go back to this sketch here. So what you're asking is, where is the position of this interface? And perhaps a little bit too suggestively, I've drawn it as though it's in the middle of the gap. Actually, what happens is that we have, so this is the steady state flow curve now of shear stress as a function of shear rate gamma dot. I've missed the symbol off here, sorry. Increases and then is flat and then increases again. Now in this regime, we have homogeneous flow. In this regime, we have homogeneous flow. In this window, we have shear banded flow. And we have a coexistence of bands of low shear rate, this shear rate here, and high shear rate, high shear rate, which is this shear rate here. And then, so what now happens, what's the difference as we track the average applied shear rate? Remember, that's the wall speed normalized by the gap size, as we track that through this coexistence region where we have a plateau in the stress. Well, what happens is that if we're at a low shear rate that's nearly the shear rate of the low shear band, then actually most of the gap is occupied by the low shear band and a small amount by the high shear band. Whereas when we're over here, most of the gap is occupied by the high shear band and only a little by the low shear band. And there will be some shear rate in here where it just happens to be half and half. Now, you ask them so that answers the first part of your question. The second part is, does that affect the linear stability analysis? And yes, it does. So a little bit oversimplistically, I've presented the analysis deliberately choosing the case where these bands are roughly equal in size. If they're not roughly equal in size, then actually what happens is that when you're thinking about the e to the ikx mode, for example, imagine we're in the x direction here, then these undulations along the interface are associated with rolls in the velocity that form in each shear band. And in fact, I'll just jump a little bit ahead to show you a picture that shows that. So we have the interface here, and then associated with that are these roll-like structures. And those roll-like structures actually have to then fit into these bands here. So what happens as the band becomes very thin, either this way, or so most of the cell would be bright, or as it becomes thin the other way, so most of the cell is, most of the cell is dark, or the other way as most of the cell is bright, is that actually, because these rolls have to fit in to these thin bands, the wavelength of the instability tends to get shorter and shorter. So that the wavelength that you see, because we have exponential growth here, e to the omega t, so everything's dominated by what happens at the peak, you find that the position of the peak shuffles around a little bit. And I think in the paper that we published on this, we did show that, but I didn't have time to show that here. Does that answer your question? And are there any other questions, perhaps, before I carry on?
She says yes at the answer to her question.
Okay. Any other questions? Okay, I'll assume not and carry on. Please interrupt if there are. All right, so we've talked about a linear stability calculation where, as I say, we have a big nasty matrix problem of the dimensionality of the discretization in Y. A linear calculation, of course, only gets you so far in that it assumes that the amplitude of these undulations along the interface is small. Now, of course, if there's a linear instability, then more or less by definition, that tells you that these undulations grow in size. And eventually they will grow sufficiently large in size that this expansion that you do, where you have lowest order, first order, higher order terms, once you've substituted into the equations and expanded, breaks down. So in other words, the very regime of the linear stability calculation that predicted the growth breaks down. And what you need to do then is a full nonlinear simulation where you basically put the model equations onto the computer and solve them, doing essentially what's computational fluid dynamics, but computational fluid dynamics of complex fluids. And I'm going to talk in a few moments about some methods that you can use for that. And if you do that, then you get these results here. So this is a steady state coexistence now, where we're again allowing spatial variations in the usual flow gradient or shear banding direction, but also undulations in the vorticity direction. And the eventual steady state has a high shear band. So this is a grayscale of the, remember the tensor WXX, which is the conformation tensor of the micellar objects. This is the XX coordinate of component of it. And in the high shear band, it's bright because the micelles get strongly aligned, and in the low shear band, it's dark. And we can also calculate the associated velocity field, which, as I've just talked about a little bit, have roles associated with that. Okay, so that's everything I wanted to say for the moment, at least, about the rheology of complex fluids. I'm going to come back to complex fluids in thinking about surface instabilities if there's time in tomorrow's lecture. But what we've done, as I said, is an overview of complex fluids in rheology. We've talked about theoretical approaches to modeling them. We've then cranked up through the spatial dimensions, talking about the flow curve relationship between shear stress and shear rate for homogeneous shear. We've said if that has a region of negative slope, then you're unstable to forming shear bands, which you can capture at the level of a one-dimensional calculation. And then if you look in higher dimensions, you find that the interface between the bands destabilizes to undulations, and associated with that, you have velocity roll fields and so on. All right, so let me just pause at this point to see if there are any questions from this complex fluids section before I carry on.
I don't see any questions.
Okay, thank you. So now what I'm going to go on to do is talk about active fluids, but through and I know you've heard quite a bit about these fluids already in this workshop, so I'm not going to spend famous last words all of the rest of the lecture talking about these, although it may turn out that way. But I wanted to do that because I wanted you to see this deliberately through the lens of looking at this from a more rheological perspective. So what I'm going to do is talk through these active fluids by deliberate analogy with the structure of the presentation in complex fluids. So I'll give an overview. I'll then talk about the basic structure of the continuum models, which, surprise, surprise, won't be too different from what we've seen in rheology. And I'll then talk through the predictions for these. So the predicted flow curve relationship of stress as a function of strain rate, if you now shear a fluid that's active. What the implications are for those curves if you allow spatial variations in one dimension and then in two dimensions. All right, so first to the overview. So here we're thinking, so as I said, my background really is as a rheologist, and I've only worked on active matter as a kind of side interest over the last few years in a sense. So my lens is to see active matter as a complex fluid. And how did we define complex fluid? Well, we defined it as a fluid that has internal mesoscopic substructures. And for a liquid crystal, for example, we said that they're rod-like objects that can point every which way in an isotropic state, or can go through a flow-induced transition to a nematic state where they're all lined up. And fundamentally, the reason that it's easy to drive these complex fluids through phase transitions by imposing a given flow is that these substructures are much larger than simple molecules such as water, and so they relax only slowly. And so you only need to shear at the rate that's comparable to that slow relaxation rate in order to drive them strongly out of equilibrium and potentially even through a transition as shown here into the nematic state. And so this is a transition that's induced by applying a globally coherent shear at the boundaries of the system from the outside. Now, here I'm drawing now an active fluid, and I'm sure you'll have heard in your previous lecture, active fluids are defined as those fluids that have internal mesostructures where each of those mesostructures has access to some energy source. So they might be biological cells burning ATP, for example, to create little mechanical stress or flow fields around themselves and propel themselves. And so in other words, we don't now have to worry about applying a global shear at the boundary, although I will then be interested in what happens when you shear these active fluids. But these fluids, even in the absence of any globally applied shear, they're out of equilibrium from within by virtue of the fact that each particle is active. And I'm sure you'll have seen then that you can get non-equilibrium ordering transitions, swarming, spontaneous flows and turbulence, and activity-induced phase separation, for example, in these active fluids. And I know that Julia Yeomans, for example, has talked about active turbulence in her lectures. So here's some experimental phenomenology, and there's an important distinction which I'll talk about in a moment on the slide between contractile and extensile systems. So an example of contractile systems is here in vitro simplification of the components of the cytoskeleton. And here you see that you get forming spontaneously rotating vortices in a pattern that looks a little bit like turbulence. And this is the velocity imaging of a suspension of swimming cells. And again, you get something that looks like a turbulent velocity field. All right, so that's the brief overview, very brief, because as I say, I know that you've heard a bit about this already. Now let's talk about the structure of continuum models for modeling these active fluids at a continuum level. Before we do that, let's remind ourselves what the basic approach was to the continuum modeling of the flow properties of complex fluids. So there we have the Navier-Stokes equation. Mass times acceleration is the sum of forces that act. There are forces due to viscous drag between fluid elements when there's a velocity gradient. There are forces due to a pressure drop, say forcing a fluid along a pipe. And so in the absence of this term, this is just the Navier-Stokes equation. And then we add that the divergence of the velocity is zero, incompressibility. In a complex fluid, we also have a contribution to the stress from the suspended substructures, the polymer chains. This depends on some structural variables, such as the conformation of the polymer chains, how deformed they are. And then we need an equation of motion for how that relaxes on a timescale tau and how it's built up in flow as characterized by the gradient of the velocity field. Okay, so that's what we saw yesterday in complex fluids. Now what about active fluids? Well, it turns out actually that the basic structure of the equation set is essentially the same. So we have the usual Navier-Stokes equation, usually approximated to Stokes by setting this left-hand side and therefore the right-hand side, of course, to zero. So inertia is not important. And we have a viscoelastic stress, which depends on a microstructural variable, which here, so these models of active fluids, as I know you've seen in other lectures, are generally built on thinking about the hydrodynamics of liquid crystalline-like objects. So we think of these particles as being slightly elongated, or there's some direction associated with the fact that they're moving or polar in some way. And so then we have this Q tensor, the liquid crystalline ordering tensor effectively. And then we need an equation of motion for how that relaxes in the absence of flow and how it builds up in the presence of a flow. So that's the basic structure. And as you'll see, it's exactly what you've seen yesterday. So there's really nothing new or mysterious about this. On the next slide, I'm going to show you a particular example, just as I did in the case of the reptation reaction model, of an equation set that has this form for an active fluid. And as I said, it's built on the notion of the hydrodynamics of liquid crystals with activity built into it. So it looks incredibly intimidating, but it's actually not. This is just mass times acceleration. These are the Newtonian terms. There's an additional stress, which is the viscoelastic part, which it depends in quite a nasty way on the ordering tensor Q. And there's a molecular field H, which determines the relaxation dynamics of that tensor. This d by dt now is, in fact, a derivative that tells you about relaxation in the absence of flow and how things build up in the presence of flow as well. And then the molecular field tells this orientation tensor whether to be in a state that points where we think of these rods, as I sketched a few minutes ago, as pointing every which way or as lining up with each other. Now, in the absence of these terms boxed in red here, this would just be a model for the hydrodynamics of rod-like molecules in suspension without any activity, no swimming, nothing, just a passive liquid crystal. There was a lot of work done extending these to active systems, and you can show that the simplest terms that then make this system active are adding terms of the form here, the most important one being this one that gets added to the stress tensor. I'm not going to go into any more details of that, and in fact it's a long time since I really thought through the details of these models, but I just wanted to show you an example that fits into this general framework and how it's made active with this term on the end here. And I think you'll have seen that in your lectures recently. Okay, so because there's a molecular field here, which, as I've said, tells these underlying rod-like entities that we're thinking of, whether they should point every which way and be isotropic or whether they should be nematic, and that depends on a parameter phi, shown in a slightly different font here and here, I'm sorry. But there's a transition built into that model, even in equilibrium, in the absence of shear, between isotropic and nematic. And what we're going to be interested in here is the rheology of this active fluid as defined by this model here in the vicinity of this isotropic nematic transition. So as I said, there's an important distinction here between so-called contractile and extensile systems. So what do I mean by that? Well, in the passive case, we just think of rod-like entities there's some director then associated with that. In these active systems, the thing that makes these systems active in this case is that there's the activity of the particles sets up a little flow field around them. And we can distinguish that according to whether the flow field is such that flow comes in along the long axis of the rod-like entity and goes out along the equator, or whether it comes in along the equator and goes out along the long axis. And the first case is called contractile, and it's denoted by value of the activity parameter, which here zeta is negative, or whether it's extensile when zeta is positive. And as I said, that activity induces this little dipolar flow field around each particle, and this has important consequences then for the collective emergent behavior of a suspension of many of these active rod-like entities in solution. So taking this model that we have and not worrying too much about the apparently very unpleasant look of all the complicated terms, but just working through those, which we've done in solving them on the computer, they're all contained in our code. You can do business as normal in terms of rheology, which is compute. First of all, you can impose that you have to have a homogeneous shear across the system, or indeed a state of no shear, which is also homogeneous and just has zero shear rate. And you can compute the flow curve relationship between shear stress as a function of shear rate. Now, what I'm interested in here is the regime of parameters before you switch on activity, where the flow curve is simply Newtonian and is a straight line through the origin. And I'm interested in that so as to avoid any flow instabilities of the kind we've been talking about so far, such as shear banding, which might come from a non-monotonicity. And I'm doing that because I'm interested in flow instabilities that stem from the activity and not from the nonlinearity of the nematic hydrodynamics. So in that regime of parameters, as I say, imagine a flow curve in the middle here, which is for zero activity, which is just a straight line through the origin. Now, what happens when we switch on activity? So again, for this state of homogeneous shear, and we're imposing that by theoretical fiat, which we can, of course, do in our calculations in the way that an experimentalist can't. In the contractile systems, what we find is that the flow curve develops a yield stress. Now, what does that mean? Well, that's kind of interesting, but I guess it's not so interesting in the sense that there are lots of passive rheological systems do this too. For example, a dense emulsion, so mayonnaise, for example, does this. And what this tells us is that if you take, say, a blob of mayonnaise and you impose it on it just weak stresses by having the mayonnaise blob sit on your plate, just experiencing the gravity associated with that pulls on its own weight, that's a low level of stress. and the blob doesn't deform, there's no shear. So that is what corresponds to this branch here, where you have what's called a yield stress. So in other words, you can impose a load to the system that's below this critical level, and the system doesn't flow, it behaves like a solid. On the other hand, when you impose a stress that's above that value, so when you take a knife and spread the mayonnaise, that's a high stress, and it makes the mayonnaise shear or flow. And so you're now at a stress above the yield stress. So that's what happens in the contractile systems. And as I've said, this is just a conventional yield stress that's seen in many passive rheological systems. And we talked actually a little bit about this yesterday, because someone asked this question of, do you always have to have Newtonian flow at low strain rates? And the answer is no, if you have a long relaxation time in the system. Now what happens, the more interesting case here to my mind is what happens in the extensile systems, because this is something that's very peculiar and isn't seen in conventional passive rheological systems. And that is that you develop actually a negative yield stress. So the yield stress here is defined, by the way, as the limiting stress in the limit as you take the strain rate towards zero. So it's the value that of this intercept here. So that's positive in the conventional rheological systems. If you take the shear rate down to zero in this case, the limiting shear stress is now negative. So in other words, we have a negative yield stress. Now, this is a very peculiar object indeed for someone who comes from the conventional rheology community without looking through the lens of active systems, because it's something that you don't find in the absence of activity. So what now is the consequence of that negative yield stress? And so now let's have a look at that. And as you might imagine, so if we now go back to, I'll just flick back briefly to the case where we had, oh, sorry, it's longer back than I thought. Yeah, so where we had the case of a shear stress as a function of shear rate that had this loop-the-loop here, we see that we get shear bands here. And the reason that this can support shear bands is that at any given stress, remember that the stress has to be uniform across the gap and common to both the bands. At any given stress in this window here, you can have a coexistence between a low shear band and a high shear band. And we talked a little bit about what stress they then coexist at yesterday. So now if we go back to the active systems, we see that in the case of the active extensile systems, we have here a flow curve. And in fact, it's more complicated than I've drawn it, because actually there's a branch here and then it wraps around like this and comes back around like that. But nonetheless, in simple terms, at any given imposed stress in this window here, in principle, you can have a coexistence of two bands of differing strain rate. And importantly, you can have a coexistence of bands of differing strain rate, even if you're not applying any stress to the system as a whole. So what does that mean? It means that you're not applying any load or force to make the system flow, but it nonetheless spontaneously starts flowing by creating a band of positive strain rate and an equal amount of a band of an equal and opposite and negative strain rate. And so when we abandon this theoretical imposition of a uniform shear, no shear in this base state here, you find that that destabilizes to give you a coexistence of a band of positive shear rate here and an equal amount of negative shear rate. And that results in a throughput along a channel. And there's no shear rate applied as a whole, so neither wall is moving relative to the other one. And so the velocity at each wall is zero. And what you have is something that's just spontaneously pushing fluid along a channel. Now, of course, this couldn't happen in the absence of activity, because there would be a serious crisis in the energy balance. But of course, what we have here is a fluid that comprises lots of active particles, each of which has access to an energy source. And it's that can then sustain this active flow field. Okay, so we've seen that a negative yield stress in the flow curve that's computed assuming a homogeneous shear flow gives rise, even at zero imposed shear rate, so stationary walls, and even at no imposed wall, so no imposed wall stress, so no shear stress on the walls, it gives rise to a flow state. And so we would call this flow, by the way, superfluid, because it's superfluid in the sense that there's no shear stress, but nonetheless you're getting a non-zero flow rate. Okay, so this is just a sketch that I've drawn. I'm now going to show you some numerical data where I'm sorry, the sketch is actually rotated by 90 degrees in the sense that here I'm plotting the velocity in the x direction. So if we go back to this, this is the x direction. So the speed in the x direction as a function of the distance y across the gap. In this case, A is where the shear rate as a whole is 0, so that the velocity of each wall is 0 because neither wall is moving. And now we get essentially the standard shear banding picture as we increase the average imposed shear rate through this window. Remember that the shear stress, which is uniform to both the bands by force balance, has to remain the same, as does the shear rate in each band, so the slope of the velocity as a function of position. And the only thing that adjusts is the relative fraction of the bands, the position of the interface, and this speaks to the question that someone asked a few moments ago. And so that once you're at a shear rate that's nearly over at the positive gamma dot plus here, most of the gap is occupied by the high shear band. So that's what happens in zero-dimensional, if you now move from 0 dimensions where you impose homogeneous shear or indeed no shear, and where you now allow spatial variations just in the direction from one plate to the other, the flow gradient direction, in other words. So this is the velocity profile here, and if we differentiate it, we get from that the shear rate. So the differential of the velocity with regards to position, as I said yesterday, is the shear rate. So now let's plot the shear rate as a function of position. So, and I fear I've apologies, I fear I've switched the position of the bands because the negative shear rate is on the left and the positive shear rate is on the right, whereas it's the other way around here. I'm sorry for that. But here we have the high shear band flowing with a positive shear rate and the low shear band with a negative shear rate. As we discussed yesterday, the interface between the bands has to have a slightly diffuse thickness, which is set by the size of the spatial gradient terms in the basic equation. So let me go back to the equations. So there are terms that are spatially local in these equations, like these terms, and then there are terms that know about space here. These spatial gradient terms then, the prefactors to these contain within them essentially a length scale, actually also with a modulus in them, but there's essentially a length scale squared hiding in these terms. And it's that length scale that sets the slightly diffuse width of this interface. In the language of liquid crystals, these are called Frank free energy terms, by the way, and they're what penalize the director in a liquid crystal from varying from place to place. Now let's look at what happens when we vary the size of these gradient terms. And I'm doing so in the left plot by fixing the activity level zeta and simply cranking up the size of the prefactor to the gradient terms, which here I've cast as an L squared grad squared, so that's emphasizing that this looks like a length here. At small lengths, the interface is quite narrow, whereas when you take this length scale that prescribes the width of the interface upwards, of course, the interface becomes very broad. Eventually, actually, it becomes so broad that the width of the interface is nearly the same as the width of the gap itself, and this spontaneous flow state is then actually wiped out to 0. So that's a way of saying that if you fix yourself at any given activity, and so this is now a state diagram of activity and the width of the interface. If you sit yourself at a given activity and crank up the width of the interface between the bands, then at a low width of the interface, you're going to have a spontaneous flow, as shown by the filled circles, and then eventually you don't have any spontaneous flow. And there's a phase boundary, if you want to call it that, between these two regions that you can show has a power half scaling. Okay, so that's for what happens in one spatial dimension. So in this plane of L, little l, which sets this length scale here, and zeta, which is the activity parameter, you have no spontaneous flow. So there would be, the velocity field would just be nothing. And then you have a region of spontaneous flow where the flow states look more like this. But of course, with a increasing width of the interface corresponds to this becoming more rounded and a blunter nose there. But you have spontaneous flow throughout this whole region here. All right, so we've got as far as more or less the end of yesterday's lecture now, counterpart of, but in the context of active systems. And we've seen that a flow curve that is multi-valued and can sustain 2 strain rate values at a given value of the stress supports shear bands if you switch to a one-dimensional calculation. What we saw in the context of complex fluids is that when you go from 1 dimensions to 2 dimensions, you get more exotic instabilities still. And in that case, the interface between the shear bands destabilized and gave you undulating states with velocity rolls in them. So the obvious question to ask now is, well, what happens when we do the counterpart of that in these active systems? So now let's do that. So here is a counterpart state diagram in the plane of the parameter L that sets the width of the interface between the bands at the level of the 1D calculation and the level of activity. So what we now do is we're not doing actually a linear calculation here. We're doing a full direct nonlinear simulation on the computer using the methods that I'm going to talk about in a few minutes, where we just put the equations onto the computer in a 2-dimensional XY plane. We're not applying any flow actually at the walls here, so there's no applied shear. We just put the equations onto the computer in the XY plane, no imposed flow, and ask what happens. And we start actually with a base state that is the 1-dimensional state that comes out of a 1D calculation. And we then ask what happens. So when we do that simulation in the part of this state diagram where there was no flow in 1 dimension, we put the equations on the computer, we perturb them slightly with 2D small perturbations, and we find that they decay away to leave nothing. So that's a computationally expensive way to calculate nothing, but nonetheless reassuring. And then when we do the same calculation, starting from a 1D base state that is the banded state that we've just discussed there, and put that onto the computer, we find that the 1D bands destabilize to give 2-dimensional flow patterns. And there can be different types of those according to the coding of the square, solid filled, hatched, or pebble dashed, I guess you might call this here. And what I'm going to show are state snapshots at a fixed level of the parameter L, which sets the width of the interface, for increasing levels of the activity in state snapshots from A to F on the next slide. So what this shows on the left-hand side is a color scale of, I think it's QXX, so the XX component of the nematic tensor Q. And on the right-hand side, which I'm not sure how it's showing up on your screen, but is the associated velocity vector arrows associated with any roll-like states that develop. And what you see is that at low levels of activity, the 1-dimensional banded state is always lost. It always breaks up to form 2D states. At low levels of activity, it breaks up to form what look a little bit like Bénard convection rolls in the context of a simple fluid that's heated from below and forms convection rolls. For increasing levels of activity, those what look like convection rolls become more disordered and wavy, but still nonetheless settle to a time-independent stationary state. And then when you increase the activity level further, so these correspond to stationary flow states, you then get time-dependent states. And I think each of these is time-dependent. And so you not only have wavy rolls, but they're also continuously moving about. And they do so increasingly so at increasing levels of the activity. So an obvious question to ask there then is, for any value of little l, and for any value of the activity, what is the typical length scale associated with these turbulently swirling rolls? Because you can kind of see by the eye, the length scale here is of order the size of the box in which you're doing the simulation in this direction. Whereas the length scale here looks to be decoupling from the box to be becoming much smaller than the box. So it seems like as you increase the activity here, recall at a fixed level of this parameter that sets the width of the interface, you're decreasing the correlation length that's associated with the size of these rolls. So when we look at that, and we can characterize that in a couple of different ways, and they both actually give the same effect. So we're just basically looking at the essential length scale that characterizes these patterns. We find that with increasing level of activity, we find a length scale that goes down as the power of the activity to the -1/2, and then it must also depend on the width of the interface between the bands. And in fact, this is the correlation length divided by that microscopic length. And you find that you get collapse of the different curves onto each other for different values of that microscopic length. So what you go from, in other words, is a regime where you have roll-like states that are on the size of the system. So this is where things are limited by the size of the system. You go into a regime where they're not limited by the size of the system. They're instead set by the size little l of this parameter that appears in the Frank constants. And the rolls get progressively smaller and smaller the more active and churned up the system is. All right, that's nearly everything I wanted to say on active matter, apart from I'd just like to spend one slide at the very end, very briefly showing actually how these two worlds can tie up even further. So recall in most of yesterday's lecture, we were talking about passive complex fluids, such as polymeric fluids, where we had a Navier-Stokes equation or a Stokes equation once this is set to 0, a viscoelastic stress that tells you about the orientation of polymer chains, and then an equation of motion for how those polymer chains behave in flow. For active fluids, we have essentially the same structure with a viscoelastic stress that crucially has active terms on the end, and an equation of motion for that mesostructure. Now, of course, many, so we've written down a model of active fluids as thinking about a model, for example, of the cytoskeleton, say, or as a model of bugs that are moving about. Now, of course, many active biological systems, many examples of active dynamics, such as swimming cells or the cell cytoskeleton, takes place in an environment that's very highly polymeric and where you actually expect to have entities embedded in the system, such as an extracellular matrix, or indeed the long polymeric filaments of the cytoskeleton itself, that obey polymeric dynamics, a little bit like the equation of motion, say, for the reptation reaction model that we wrote down for the living polymers before. And so what we did in this project here was to write down a model that actually unifies these two worlds by having the momentum balance equation as before. The stress tensor has the pressure term and the Newtonian term. It now has a term with Q-sector dynamics, which is sort of the active entities, the active liquid crystalline part of that. And that's exactly as before, the model that we've written down a few slides ago with all the complicated molecular field terms, for example. And we now also have a polymeric stress, which obeys an equation of motion, which actually here happens to be the Johnson-Sageman model, but it looks very much like, for example, the reptation reaction model of worm-like micelles, which can also be a model of unbreakable polymers too, in a certain limit. So basically what you're doing here is combining a model for the rheology of passive complex fluids with a model for active pneumatics, so yesterday's talk and today's talk. And one thing that's then fun to do is to ask, well, what happens when you're in the backdrop of a complex fluid? So remember, a complex fluid has a relaxation time associated with the reconfiguration dynamics of the polymer chains. We denoted that tau. You can actually take that relaxation time to be as large as you want. And when you take the limit of that relaxation time to infinity, you actually have a complex fluid where the stress never decays. And that's actually an example of what's called an elastomer, or it's effectively showing solid-like behavior. So what you can do is ask about what the dynamics of embedded active entities are in a backdrop that's actually elastomeric and has no relaxation time associated with the polymer. And what we found here was that actually you get a state of what we called, slightly regrettably, because it actually clashes with terminology that's used in the polymer literature for viscoelastic turbulence, but we call this an elastic turbulent state because this is a turbulent flow field that's taking place in the backdrop of a system that actually has a solid modulus to it with an infinite relaxation time. And in consequence of that, this turbulent field can only ever be there transiently. And as time progressively increases, you find that this turbulence gradually coarsens its way out to leave you eventually with no turbulence at the end of the day. So that was just a fun aside showing that you can actually combine these two worlds of rheological models of complex fluids and of active fluids. Okay, so to summarize then, we've so far talked about the rheology of complex fluids and the hydrodynamics of active fluids. In each case, we've given an overview, we've talked about the structure of continuum models, and then we've done a study in bulk flow instabilities where we crank up through the spatial dimensions, first of all imposing homogeneous shear, then allowing a 1D shear banded state, and then allowing 2D perturbations, which in the case of the worm-like micelles led to an undulating interface between the bands with velocity rolls within each band. And in the active fluids led to more complicated 2D states, still including active turbulence. And each of these has essentially been a study in bulk flow instabilities. What I'm going to spend a few minutes, and I'm going to pause for questions in a moment, but just to outline the rest of the lecture, probably for the rest of today, we may end up finishing a little bit early actually, which is fine because it allows lots of time for questions. For the rest of today, I'm just going to give a relatively brief interlude that outlines in practical terms how you set about putting onto the computer these continuum models of complex and active fluids, because I thought, well, this is a summer school and you're coming to learn some practical methods as well as the backdrop theory. So I thought it'd be useful to have a quick tutorial in the kinds of numerical methods that we use. That'll take us to the end of today. And then so far we've been focusing throughout on instabilities that occur within the bulk of the fluid, and we've not really been thinking about the fact that the fluid has an interface with the outside air. It actually turns out that in experimental rheology, so this is going back to the passive complex fluids, that very often we have instabilities not only that arise within the bulk, such as shear banding, but that arise where the surface of the fluid sample that you have meets the outside air. And we're going to talk through some of those instabilities in tomorrow's lecture. So before we dive into the numerical methods, I'm going to pause now to take any questions that you might have on the section, either on the active fluids today, or if there are any remaining questions from the complex fluids yesterday as well.
I have a quick question about the 1D active pneumatic system.
Yeah.
So if I understood correctly, the phase space was showing us whether the V equals 0 state was stable or not.
Is that this?
Yeah,
this
yeah,
yeah.
this one. So now I guess I'm wondering if we started in the V equals 0 is stable state, but the initial condition was the Poiseuille-like flow down the channel. I was wondering if that would relax to a V equals constant state down the channel, or if it would just relax to the V equals 0 state. Are those two different in the active pneumatics situation?
Yeah, that's interesting. So by a V as constant state, I think you're meaning, so a V as 0 state would correspond to the velocity vectors here having 0 length, so there's no flow down the channel. And I think, correct me if I'm wrong, please, but I think by a V as constant state, you mean these arrows all have the same length. So there is a flow through the channel, but it looks like a plug flow.
Yes, exactly.
Yeah, okay, thank you. Yeah, so such a state would be a possible solution if you didn't have to worry about the boundaries, because actually those two solutions would have to be the same by Galilean invariance if you didn't have to worry about the boundaries. But you also actually have typically, and this is something that theorists blithely do, typically what you do is impose a no slip condition where you say the velocity of the fluid at the wall has to match the velocity at the wall, and in this case that's 0, the balls aren't moving, and so actually that wouldn't be consistent with a plug flow along the channel because of that boundary condition. What we'll actually come to see in tomorrow's lecture is that very often that condition of wall slip of 0 slip is actually simply not met at all, and you very often in experiments in rheology get very, very strong slip at the wall of the cell. And actually there's been 30 odd 40 years now of energy devoted to deriving constitutive equations for what happens within the bulk of the flowing fluid. That's these equations that I've shown you. Actually, I think there's another, if anyone wants the task, and there are some people actually who've done some nice work in this space, but it's been a lot less well turned than the bulk modeling, is to develop constitutive equations for what happens to the layer of complex fluid particles near the wall, and actually how what you'll have is not just a static boundary condition at the wall, but you'll actually have almost like a wall equation of motion that then has to match up with the bulk equations of motion in quite a complicated way. But that's a good question. Thank you. Yeah.
Thank you.
Hi, I was wondering if you could say some more about the structural tensor that goes into the theory in the case of like non-pneumatic active matter.
Yeah, so this is something I haven't drilled down into recently, actually, and at the time that I was, so it's a few years now since I've worked in active matter, and I'm much less of an expert in this than I am in complex fluids. So I guess in the case where you really have elongated particles that are swimming, and I should say I'm talking slightly more off the top of my head here than I am for most of the other answers to the questions, but I guess in those cases you might actually have the particles lining up with each other, even in even if they're not active. And then you would genuinely have particle alignments, which is what then is captured in this Q tensor. Now, there's then a question of principle, I guess, is if you take spheres, spherical particles, that nonetheless swim from place to place, there's obviously then a little direction vector associated with the direction in which they're swimming, or indeed, even if they're not swimming from place to place, but they set up a dipolar flow field, there's still a director associated with that, a headless vector. Now then, is in some sense, is this tensor telling you about the orientation of that? Well, maybe so, but then how do you take the limit of that when you switch off the activity and there's no swimming? So this is a question I remember asking myself, actually, of the people who sort of forged the field in active matter a few years ago. And from recall, what I got was the answer that actually that's a very interesting and open question. I have to confess, I haven't followed the field enough recently to know where that's got to. And it may be that is Julia Yeoman still with you this week? It may be, is Julia in the audience here? Maybe that Julia has a better answer than I do to this.
No, she headed back home.
She's back, yeah, okay.
Okay, we have one more question.
Yeah, hi, Professor. Thank you for your lecture. Maybe I missed it, but I'm interested in the shear bands. I'm wondering whether that could be susceptible to barotropic or shear instability, which is an inviscid instability. Is it possible?
So I think I caught the word inviscid instability. There was another word. Was it barotropic instability?
Yeah, just shear instability. I mean, we have a first necessary condition, and for example, we have a jet-like structure as you showed. I think that could be barotropically unstable or shear unstable.
Yeah, so I don't know so much about those instabilities. I'm sorry. I used to know at the level of having taught some undergraduate courses that involve that, but that's years ago. So I'm sorry, I'm really not well placed to answer that. In terms of whether there would be an implicit instability, I guess not, because actually these are very highly viscous materials.
Oh,
so
highly viscous.
Yeah. So you're always thinking of the regime in which viscosity is far more important than other terms in the system. So I would guess not, but again, I don't think I'm particularly well qualified to answer questions, certainly anything to do with barotropic instabilities.
Yeah, got it. Thank you.
Okay, thank you.
Okay, one more question.
Hi, so I also have a question about this shear bending. So I feel this shear bending is similar to the first order transition in equilibrium statistical mechanics. So I'm thinking about this development of the two bands are like a nucleation of nucleation phenomenon. So if we increase the shear rate from below, I assume that the high shear rate band would appear in either the upper boundary or lower boundary. But it seems the picture you show that is you always put the high shear rate band on top. Is it possible that the high shear rate band appear in other position?
Yeah, thank you. That's a good question. So let me go back to the shear banding sketches, since that's what we're talking about mostly. Yeah. So this is the sketch you were talking about, I think. So in this sketch, actually, up and down don't really mean anything, in the sense there's no gravity in this system, we're assuming. So you could equally well have the high shear band here. And this is also assuming completely flat plates here as well. So there's nothing to tell you anything that's different from any position in the cell compared to the other, apart from the fact that you have the walls here with no slip condition. So actually, at the level of a theoretical calculation, if you do a theoretical calculation in this 1D geometry with a homogeneous state and with initial perturbations, what you can find actually in this exactly planar geometry, where the shear stress is exactly uniform across the gap, is you can find you get multiple bands of high shear rate that can form. just as when you think about, for example, the spinodal decomposition of two fluids that are initially mixed and then demixed when you drop the temperature, which I think was the example that you alluded to, just as there you can get multiple, excuse me, I'm very sorry, my telephone's ringing. I'm sorry about that. Just as in the two-phase system where you have spinodal decomposition and where you get droplets of one phase forming in a backdrop of another, you can have multiple droplets. Now, what happens in the spinodal decomposition example is that those droplets that then coarsen, there's a sort of Ostwald ripening type of process where you get diffusive and then viscous and then hydrodynamic regimes of coarsening, which has been pretty well turned in model H, for example, in this model classification system of hydrodynamic two fluid models, say. Now, the counterpart to that here would be that you would then get a coarsening of these bands, but it turns out actually that coarsening is very much slower in a one-dimensional system than a 2D system, and that's because coarsening is driven effectively by the surface tension of the droplets in the 2D case, that you don't have that curvature of the droplets driving that here. This is all actually a very waffly way of saying that that simple 1D calculation where you have exactly planar plates in the theoretical case isn't actually particularly relevant to any real experiments. And that's because a real experiment, well, it is relevant, but only at first order, because actually in a real experiment, as we've said, there's almost always some curvature to the flow device. So in other words, you would almost always have a curved plate here and a curved plate here, and we're just seeing a little section of it here. What that curvature means, and you can actually do this by solving even just the Stokes equation in a curved device, is that the stress that you get is slightly higher here than it is here. That means that if you look at the stress where you are in the flow curve at the inner cylinder, if this is the inner cylinder and this is the outer cylinder, the inner cylinder, the stress is here and the outer cylinder is here, and that always tends to favor the high shear band to form at the inner cylinder. So in fact, if this were the inner cylinder and this were the outer one, the high shear band would be there. Does that answer? And in fact, when we look at the experiments here, indeed, this is the inner cylinder here, and this is the outer cylinder, and this is the high shear band, and this is the low shear band. So does that answer your question?
Yeah, you got it. You got a yes. Any more questions?
Thank you.
I think that's it.
Okay, good. All right, so how are we doing for time? So I guess the numerical method section probably won't take more than 10 minutes. That'll take us up to 20 past. I think if it's all right with you, I'll then break at that point, partly because my voice, unfortunately, these days doesn't seem able to, at least over Zoom, talk for more than an hour and a quarter or so. And then it also gives us a fresh start tomorrow in the surface instabilities, which is quite self-contained. So famous last words, the numerical methods might take the full time anyway. Okay, so the numerical method. So let's remember the structure of the equations to be solved. So we've said that we have an extended Stokes equation. The terms are written in a bit of a different order here, I'm sorry. But so you have the viscous drag terms, the pressure gradient terms, and you have the extra stress, which I think actually I denoted little sigma earlier in the talk, and here is big sigma. I'm sorry about that, but hope that doesn't lead to confusion. And also, I just spoke in words previously that the flow is incompressible. Now let's write down the maths for that. It says that the divergence of the velocity field is 0. So this is the Stokes sector, force balance and incompressibility, and then you have a viscoelastic constitutive equation. And previously I muffled all of this stuff here into this big nonlinear n as a function of E and grad V. And I could do that because actually, as I said, I wasn't committing to whether n was local or non-local. Of course, you can see now that it's non-local because you have these spatial gradient terms, which in the context of a liquid crystal would be Frank-like terms. But here I'm more thinking of polymeric viscoelastic constitutive equation, where this is the term that sets the slightly diffuse width of the interface between the shear bands in where might my cells say. So, and this D here, I should say, is just the symmetrized part of the velocity gradient tensor grad V. And I've written this out a bit more fully, and previously this derivative on the left-hand side was all smuggled into capital big D by dt. Here, you can see that this derivative now is the derivative that accounts for the fact that any fluid element changes in time, not only because the fields themselves might be changing in time, but also even if the fields aren't changing in time, a fluid element is moving from place to place. And if you have spatial gradients, you then get changes in that fluid element. Okay, so that's the basic structure of the equations. And what we do in the code is that we have two time steps. So in the first time step, what we do is solve the Stokes sector here. And we do that by fixing sigma to whatever it is from the previous time step. And for that sigma, then computing what V and P have to be. And in fact, we don't really care what P is in most calculations that we do, but we do need to think about P because it's needed to enforce incompressibility. And so we solve this Stokes equation to get the velocity. And then in the second substep, at any given time step, is we feed that velocity that came out of the previous substep into this sector here. And then with that velocity fixed, we then, which is fixed therefore here and in the symmetrized part of this grad V tensor here, this G is just a constant, as is this relaxation time in this L squared. We then update sigma at that fixed V in this second substep. So I'm now going to just talk a little bit about some of the practical methods for doing each of those substeps. And I should say I'm cheating a little bit because I'm describing here only methods that we've used in periodic domains, and it's actually a little bit more complicated generally to do stuff in closed channels, but I'm going to just give references later on for how to make the switch to looking at closed channels. Right, so let's work through those substeps in turn. So the first substep, we solve the Stokes sector. So let's think about the Stokes sector. So the basic question here is, given any stress field sigma, how do we compute what the velocity has to be to satisfy these two equations? Okay, so these equations, as you can see, are linear. All these terms here, they only have one multiple of V or P or F. And I'm writing the divergence of sigma, by the way, as F, because the divergence of a tensor is the form of a vector, and this suggestively looks like a forcing vector, which is more or less what it is, in fact. So these terms are linear. They're also non-local. So there are lots of nasty gradient operators in here, which can be a headache to solve using finite differencing. So what we do is handle that in Fourier space. And this is where obviously it helps to be in a periodic domain where Fourier components are very convenient. So we handle this in Fourier space. And to do that, then we convert all these fields take the Fourier transform of them, and to do that we use fast Fourier transform techniques, and indeed there's just a package online called FFTW, and that's freely available to download, and we use that. So having taken the Fourier transform, so V of x and t becomes V of k now, and the grad squared operator turns into ik squared and the gradient into ik. So we have these equations, which if we now then take the divergence of this first equation, we find obviously the divergence of velocity is 0, so that first term goes away. And so then we can just rearrange these two terms having taken the divergence, and that enables us to find the pressure, which, as I say, we're not desperately interested in usually, but we do nonetheless need it because it feeds back into what the velocity is. So now we know the pressure, and we feed that into here. So we have a term now that knows about V, and a term that via the pressure now knows about F. So we can then rearrange that to get the velocity at any wave vector k is written as a linear operator at any k mode, which is kind of local in k now, even though it's not local in position. And that is a tensor that gets multiplied by the forcing field, the divergence of the stress, which recall because we're fixing the stress to what it was at the previous time step in this sector. Now this tensor before, you've seen before, I think in Julia Yeoman's lectures a week or two ago, this is called the Ocean Tensor, and you only need to calculate that once at any wave vector k. So that's just a tensor that's known at any wave vector k. So actually, once you've taken the Fourier transform of the forcing here, forcing vector, and you can either compute F being the divergence of the stress tensor by taking the divergence in real space and then taking the Fourier transform of that, or taking the Fourier transform of the stress and multiplying it by IK. And so that then gives you the velocity in terms of the forcing that comes from the divergence of the stress. And then all you do then is take a Fourier transform back into real space and you know the velocity field. Okay, so we've now done the first substep, which is to solve this Stokes sector for a fixed value of the stress. Now that gives you the velocity, you substitute that into here, and you want to now time step forward the constitutive equation at this time step to now update the stress. So how do we do that? So, the second substep is updating the dynamical equations now at fixed V, the viscoelastic constitutive equation. And recall, we talked through the structure of that constitutive equation, which has this term needed to tell you about advection as a fluid element moves from space to place. You've got these terms which simply contain the gradient of the velocity tensor, but don't contain any spatial gradients. There's no gradient operator here other than that you have grad V in here, but you're not taking any gradients of the stress, crucially. And then there's the gradient term here where you're taking the second, the grad squared of the stress. So basically, okay, this is tensorial and it looks nasty, but actually in terms of the numerical challenges, you can capture those in a simple scalar equation, which I've color-coded correspondingly. And this simply says that partial d by dt of c, which is now just a generalized variable, which let's just say it's a scalar, is v dot grad c plus a term that actually, once, because you know what the velocity field is, so I'm not even writing that in here, it's just some nonlinear function at any position in space of itself, of c, and then there's a term grad squared c in here with a prefactor. So basically there are three types of term. There's a spatially non-local quasi-linear advective term, linear in the sense that it's linear in C. There's a spatially non-local linear diffusive term, and there's a spatially local but non-linear term. So what we do is use different numerical methods for each of those, and to do that we do what's called splitting the operator. So we just simply update each of these terms in turn. And I'm going to illustrate this in one spatial dimension, but it very easily generalizes actually. So let's look at these terms in turn. So first of all, which term are we going to look at first? We're going to look at the spatially local term here. So in numerical essence, at fixed grad V, and grad V is what determines D, remember, all we have is d by dt of sigma is equal to some non-local function of sigma. So in scalarized terms, d by dt of c is f of c. Now, this could be the introduction to any course on numerical methods, because this is just solving an ordinary differential equation at each grid point in your code. So there's nothing fancy about that at all. It's basically just an ordinary differential equation at each grid point I. So you discretize that in space, and you can actually even do that simply using the explicit Euler method, although you can use more sophisticated methods such as Runge-Kutta, which means you can use a larger dt. But I've just written the formula here for the explicit Euler, and that says that, so you discretize the time derivative to say that at any grid point I, from time step n to time step n.1, n plus 1 divided by dt, that's the derivative. And that's specified, and the explicit nature in here comes from saying that this is evaluated at time step n rather than n plus 1. You then simply rearrange to get what it is at time step n plus 1. So that's as simple as can be, really, although that's the simplest algorithm you can think of using. All right, so you then have the second kind of term, the one in red here, which is the spatially non-local linear diffusive term. So that's basically what we're doing here, is solving something that looks like a diffusion equation once we've trimmed out all the rest of the stuff. So that has this form in real space, which is a bit of a pain to solve because this is a non-local operator. But of course, and I cheated a little bit by putting ourselves into a biperiodic domain where we can work in Fourier components. But again, if you take a fast Fourier transform of that, you get something that's then diagonalized in K in the way that it wasn't in position. And this just is then, it can be solved separately at any given K. And it turns out, because of the diffusive nature of this, it's best to use a semi-implicit algorithm. So we discretize the time derivative as normal, but instead of being explicit, which would involve only having terms in C evaluated at the present time step n to move to the next one, n+1. If it were fully implicit, you wouldn't have that term, you would just have the n+1. Semi-implicit means you take the average of those two. Nonetheless, still, what you have here at any k is an equation that you can simply rearrange to get c at time step n+1 in terms of c at the previous time step. As I say, you can use other time stepping algorithms too. And then once you've done that at each k, you then take the Fourier transform back into real space. And then finally, you have the term in green here, which is the v dot grad c. Now, this is spatially non-local because you're taking a gradient of v. It's quasi-linear. Okay, it's not linear in the sense you're multiplying v and c, but remember, v is just fixed in this sector of the dynamics. So you're basically interested in solving d by dt of c as minus some velocity field, which is known and fixed, dotted into the gradient of c. Now, what you do, so this is an advection term, and this basically moves information in space according to the direction of the velocity field. So it's like a current moving information that's being wafted along by the velocity. So depending whether the velocity is positive or negative, it tells you whether information is moving to the left or right, if this is just being done in one dimension. So what you use to allow for that asymmetry between positive and negative v is what's called an upwinding algorithm. You can use first order upwinding, and sometimes we do. Actually, what we found that caused horrible problems in the shear banding interface destabilization code. So we switched there to using third order upwinding and Euler time stepping. So as usual, discretize the time derivative of c in the same way. And then we discretize this by taking a third order spatial derivative of c, which depends on whether v is positive or negative according to these two terms here. And this is the discretization of that derivative at third order. And you can find how to do this is just written down in numerical recipes in C, I think, or Pozrakidis's book on fluid dynamics. Okay, so that's a summary of the numerical method. So we use time stepping and finite differencing in real space, along with taking Fourier transforms, particularly to handle non-local diffusive terms. So specifically, we handle spatially local nonlinear terms in real space, spatially non-local diffusive terms in Fourier space, advective terms in real space using third order upwinding, and we handle the Stokes sector, which I talked about first of all, using the Ocean Tensor in biperiodic flow in Fourier space. As I've said, all of that has been made easy by the fact that we can take a Fourier transform in both dimensions because we're thinking about a biperiodic box, or it would generalize to triperiodic. If you're in a channel where you have closed walls, things get a bit more complicated, but these methods are all very well established. And I've just given here some books that give you practical guides to do that. All right, so that's the end of the interlude on numerical methods. And I'm going to close there. I think we're 5 minutes early. That leaves time for a few more questions if there are any. And then tomorrow we'll return to the world of complex fluids and now think about instabilities that happen where flowing complex fluids meets either the outside air or indeed the walls of the flow cell. Okay, so thank you very much for your attention. Are there any more questions for today?
Yeah, there's a question here.
Hi, when you said you use Fourier methods for the Stokes sector, you did not assume walls, right? Because
no, exactly.
There are,
yeah.
Okay, so it's periodic boundary conditions.
That's right, yes. Yeah.
Yeah, okay. Cool.
Yeah, as I said, it is more complicated if you've got walls, and these books here contain lots of advice on how to handle that. Yeah. But I didn't really have the space in these lectures to go into that more complicated stuff. Yeah. Typically what you do there, by the way, I mean, we have done that, is that what we do is in one spatial, say you've got fluid flow through a two-dimensional channel where you've got periodic boundary conditions in the x direction and closed walls in the y direction. So something that looks like, something that looks like this, where you might have periodic conditions from this side to this side, but closed here, is that we take a Fourier transform in this direction, but then we actually finite difference in this direction. So in fact, the paper where we wrote up this stuff on, wait a second, I can't find it. Yeah, the paper where we wrote up this stuff, which I handily haven't given a reference for, I think it's in PRE in the, just before 2010, maybe 2009, we actually write down the numerical method for that in all its gory detail there. Yeah.
Any other questions? Yep.
So this is perfect because you already have the slide pulled up. In these 2D undulations that happen in the passive fluid case, you showed us, that there's a most unstable wavelength and that the growth rate is greater than 0. But is there an intuitive way to think about why these undulations form? And maybe it's related to the velocity rolls, and also what sets sort of the steady state amplitude of those undulations.
Yeah, two very good questions. Let me talk about that. If you don't mind, I'll talk about why you get undulations with wave vector in the x direction, and then it's a kind of not too distant step to why you get them with wave vector in the z direction. So there was some beautiful work done by the Cambridge group, so John Rellis and John Hinch, and who was then a PhD student, Helen Wilson, who's now actually head of maths at UCL, who did lots of work studying the instability of layered fluids. So not there in the context of shear bands, but if you think about it, shear bands almost look like two layered fluids. So let's think about two layered fluids where you have different normal stresses between the fluids. So by that, the normal stress, remember, and for the x direction, the relevant normal stress is the xx minus yy stress. Now I'm trying desperately to think back to the mechanism here, and I'm probably not going to get this exactly right, but you can read up about it in Helen's papers from around the time of her, in fact, her PhD thesis was on her website. But basically what happens is the nub of the issue is that there's a jump in the size of the first normal stress across the interface here. Now that's consistent with force balance, so that there can't be a jump in the shear stress, but there can be a jump in the normal stress. So long as the interface remains perfectly flat, that's perfectly consistent with force balance. Now imagine you get a tiny amplitude undulation along the interface. You now have a jump in the size of the normal stress, but that now the normal stress axes somehow are oriented this way and this way. So what that does is actually create a little flow field that pushes fluid slightly round. And here is where I'm getting a bit hazy, but it pushes fluid slightly round. And then incompressibility tells you that the fluid has to recirculate, and it recirculates such as to push down on the next trough next to the point that I've just been talking about. So there's basically a positive feedback to do with the fact that you have a jump in the normal stress. And it's the jump in the first normal stress that gives you these undulations with wave vector in the x direction. As you might anticipate, actually, it's the jump in the second normal stress that gives you undulations with wave vector in the z direction. Yeah. And then I think you asked about the wavelength of the steady state undulations, and I don't have a quantitative answer, but it's basically to do with the fact, and I think I talked about this a little bit in response to one of the other questions, is that once you have the steady state here, you have velocity rolls, and those velocity rolls they already look a bit squished here, right? Because you have this wavelength and then they have to somehow uncomfortably circulate in this very squished direction here. And it's somehow that then tells you, for any given width of the band here in 0 dimension, it's that somehow tells you what the wavelength is in this direction. But I don't recall every last detail of that. I'm sorry.
Okay, one more question.
Hi, so you talked about the numerical methods in terms of time-stepping algorithms. Have you looked into solving directly for the steady state?
No, actually, we haven't. No, we always do time stepping. Although if we're not interested in the dynamics, then typically what you can do is get to the same steady state faster by using a slightly higher time step, which maybe throws away some of the dynamical information, but typically gets the steady state okay, has been, roughly speaking, my experience, but that's a little bit hand wavy. But no, I mean, there are methods that you can use, I think, where you, I don't remember exactly what they're called. Are they shooting methods or something, where you start from one wall and you just try and solve the d by dy, hoping to get to the right place at the other wall, and then there's a condition that you have to match up between the two. I haven't actually looked into those at all. I think Helen did actually use those in her PhD thesis, actually, on the layered instabilities, I think. So you might want to have a look at that, but I can't remember more details than that. Yeah.
Any final questions? Okay, let's thank Suzanne for her lecture.